Welcome to Made in Science, the official podcast of the University of Stuttgart. Today we are going on a trip to the future, together with Professor Joris van Slageren, who has been professor at the Institute of Physical Chemistry at the University of Stuttgart since 2010. Other stops in his research career have been Utrecht, Amsterdam, and Florence, but we'll hear more about that. Some keywords in his scientific world are molecular magnetism, molecular nanomagnet, molecular quantum bits, or molecular spintronics. Now, this is not science fiction. This is a podcast on the impact of research in chemistry on quantum science in the research project called Chem for Quant, which is one of the current submissions of the University of Stuttgart for the next excellence strategy. Let's hear more about it. First of all, hello, Professor van Slageren, and thank you very much for being with us today.
Thank you very much for having me, Dr. Holtkamp.
Now, my first question is, in how far is your research different from quantum physics?
Quantum physics is a wide field with, so far, a long history, which has moved now from basic science, where people have looked at the quantum properties of matter and radiation, keywords such as quantization, entanglement, and superposition, to developing real-world applications. So far, chemistry has played an important role in these developments, in the sense that some of the materials studied in the realm of quantum physics are made by chemical means. For example, diamond nanoparticles or two-dimensional materials. But one part of chemistry has so far been neglected, and this deals with molecules, the use of molecules as units in quantum technology, so-called quantum bits. And this is exactly what my group does. So we design, we synthesize and investigate molecules that can serve as the smaller units in quantum technologies called molecular quantum bits. And this, we believe, is a very important contribution to quantum science and technology. And because of that, we are trying to develop this on our own, but also together with other people.
How did the title Chem for Quant came about in this context? I do understand the relation now much better already, but what does the title suggest in particular?
This is the collaboration that I was referring to, which is Chem for Quant. The full title is Chemically Designed Quantum Architectures, which is a proposal for an excellence cluster in the current excellence strategy. The concept behind this proposal is that we will use chemistry to design novel quantum architectures, which starts from these very small units, the molecular quantum bits, but then proceeds to assemble these units into regular arrays or in few quantum bit structures, which can be used then or incorporated into quantum devices. So it is an initiative which, of course, then spans a wide range of expertises, which is important in our view to achieve our goals.
In the context of your work and in preparation for our conversation, I came across a couple of terms. One of them is qubits. Could you explain what that means? And perhaps there are other terms that we need to understand to fully grasp actually what you and your research group are doing.
Qubit is, of course, the central concept. In our computer today, the basic unit is the bit. It is a digital device, and a bit can have two states, which we call typically 0 and 1. And we can encode information in these bits, and these bits are used to implement algorithms, make computer programs, and so on and so forth. The fundamental difference with a quantum bit is that a quantum bit cannot only be in a state which we can call 0 or a state that we can call 1. It can exist in a so-called superposition state, at which point the quantum bit is in the states 0 and 1 at the same time, simultaneously. And this allows us to to devise algorithms which are not possible with conventional computers, which would allow us to do certain calculations which will not be possible within the lifetime of the universe using conventional computers, however fast they may become.
The task and the challenge in this, I think, is just huge. And I would imagine that collaboration is very important in this matter. So, in your research, how important is the interdisciplinary approach?
Interdisciplinarity is absolutely crucial. We try to cover some of these disciplines within my group, but this is certainly not sufficient to achieve our goals. And this is also, of course, why in Camp for Quant we have teamed up with many researchers in the Stuttgart and neighboring cities to achieve our goals. And the range of expertise involved spans all the way from synthetic chemistry, but not just synthetic chemistry. We are considering different materials. So we will need experts in certain types of organic synthesis, in certain types of complex synthesis. We will need theoretical chemists that can predict the properties of the molecular quantum bits that we are going to synthesize, so that we can have a blueprint of which molecule is our target molecule. We will need experimental physicists to measure and understand the properties of the quantum bits on an individual level, but then also later on in the assemblies of quantum bits that we are trying to develop. We will need theoretical physicists, not only a theoretical physicist, but for example, a theoretical physicist that can tell us what the influences of the surroundings on the coherence, so the lifetime of these superposition states that I alluded to before, are, but also quantum physicists that can tell us how to manipulate these quantum bits, how to implement the quantum algorithms that I spoke about before. We even have included information scientists, people that can understand on a much more fundamental level how to build compiler structures. And we hope that they will be able to tell us how to actually arrange different quantum bits, how to make sure that they are coupled together, how they interact with each other. So this is a hugely interdisciplinary proposal and project, which of course is very much in tune with the way Stuttgart, the University of Stuttgart, sees itself. The Stuttgart way, of course, is to promote interdisciplinary research.
So does that mean that the University of Stuttgart has it all, everything you need for your research to come to good results?
The University of Stuttgart, of course, has a wide range of expertise that is relevant for this endeavor. It has a long track record in working in quantum technologies. However, for this proposal, we need more than the University of Stuttgart can offer. And that is why we have teamed up with our neighboring universities at Ulm and Karlsruhe in order to make this a success. Researchers in these institutions provide additional expertise, which is absolutely fundamental for this cluster proposal. The University of Stuttgart and Ulm have already worked together in the field of quantum science and technologies for about 20 years already, and of course have their, in that sense, a proven track record of being able to successfully cooperate across institutions and across disciplines. Now, with this particular project, we needed additional expertise, which was only available at Karlsruhe, and therefore KIT is now strongly involved and are actually leading this particular proposal.
In your excellent research career, you have come to Stuttgart twice, actually. Please, could you tell us about your experiences on the road that led to Stuttgart, then away from Stuttgart, and then back again?
Yeah, this is actually a funny story, and it was completely unplanned. So at the end of my PhD, which I did in Amsterdam, where I'm originally from, I decided it was time to do a postdoc abroad. And I tried to combine excellent science with a reasonable place to live. This is what we call nowadays work-life balance. And this led me to Florence in Italy, which of course is a beautiful city where there happened to be this fantastic research group in molecular magnetism where I did a 2-year postdoc. Now then at the end of a postdoc, it is time to move on. And I have done anything right in my scientific career. It's always that I have managed to move on when it was time to move on. And therefore, it was time to look to next opportunities. And at that point, of course, one realizes that the academic career is a long and stony road in order to get a permanent position. And therefore, I started to apply also in industry, and I was interviewed a number of times, but I did not feel that this was the right way for me to go. Then there happened to be a job advertisement for a position as a postdoc in Stuttgart in physics, with the possibility to build up my own group. And I asked Professor Gatteschi there in Florence if this was a reasonable group, and he said, they are physicists, but otherwise fine. So I applied, I was interviewed, I gave a presentation and was offered then the position. And this has allowed me then to build up my own group in molecular magnetism and finally do my habilitation degree in physics. And then after 5 years or so, it is time to move on to become professor, or at least to have a permanent position at a university. And I applied at different positions in Germany and was interviewed a couple of times, but I was never offered a position. And then, impatient as I am, I started to apply more widely. I was interviewed at ETH in Cambridge, and then finally I was offered a position in chemistry again at the University of Nottingham in the UK, where I had a very, very good time. It was good to experience yet another culture and also academic culture, and I learned many things during my stay at Nottingham. But then this job advertisement at Stuttgart in chemistry, in physical chemistry, came up, and I decided, because previously I was slightly annoyed that I was not offered a professorship in Germany, I decided to apply for this position in Stuttgart to see how far I would get, having my habilitation, applying from a permanent position in academia. And of course, as they say, one thing led to another, and I was offered a position in Stuttgart, which I then took only after only 3 years in Nottingham. Of course, in retrospect, with Brexit and so on and so forth, this was absolutely the right thing to do, to accept a position in Stuttgart. And of course, since 2010, I've now been here at this university.
At all these various universities and institutes, how did you experience quantum physics? Has it been a game changer? Or do you think that Chem for Quant is the real game changer in the field of computer storage and application?
I think quantum physics has come a long way. It has moved from basic science to applications in fields like quantum sensing, where starting from next year, commercial sensors will be available, also being sold by major companies, also in the Stuttgart area. I think in other areas of quantum technologies, especially quantum computing, there are hurdles looming on the horizon which are not so easily overcome. And this has to do with what is called in the field scalability. So the number of qubits that I can sensibly put together and that will interact with each other in a meaningful way. And this number appears to be 1,000 at the moment. And it is not easy to see how we are going to get from 1,000 to 1 million, which is really the number that you need to make a difference in quantum computing. And we believe that the chemical approach, which allows us to make many equal copies of quantum bits, molecular quantum bits in this case, and we believe that we can position these in a way such that they will interact in the right way. We believe, therefore, that the quantum approach will allow us potentially to overcome this hurdle and to arrive at quantum processors with millions of quantum bits rather than hundreds or thousands.
In your life, when have you first developed an interest in molecular chemical research? You are very fascinated by your work. You have a vision what to achieve. But when did all of this start, actually?
This was during my undergraduate days. Of course, chemistry is largely molecule-based, so the molecular aspect is not so new or astounding. It was during one of the lab courses that I spent the last 3 weeks of this lab course in a research group making new molecules and the fascination of making something that nobody has ever made before, to hold in your hand something which is the entire amount that exists in the universe of this particular compound, this fascination has never left me. So I did a research project then in catalysis, trying to make chemical substances in a more efficient way, when I realized that the reaction mixtures had different colors. And I realized that in my analytical chemistry, there are these spectroscopic techniques to investigate different colors, to convert what we call a color into a curve, a measurement curve, which we call a spectrum. So I went to a neighboring group, got myself the equipment to study this in more detail, and I have been a spectroscopist ever since. The interest in quantum came, I would say, after my PhD, when I decided to move fields to things that were more in the direction of physics. And this started with molecular magnetism, the idea that you can make molecules that can be used to store information. And then about 15 years ago, I moved more and more in the direction of molecular quantum science, looking at physical phenomena such as quantum coherence and how this can be implemented and understood in molecules.
I already know that you are also a fan, like myself, of science fiction literature. So I would like to extend and explore a little bit on that one. In the 1960s novel Slaughterhouse-Five, US-American author Kurt Vonnegut writes about an encounter of his protagonist Billy Pilgrim with beings from the planet Tralfamadore. He cannot read Tralfamadorian, but he tries to understand their literature. The use of words is explained to him in the following way, and I quote, "We Tralfamadorians read them all at once, not one after the other. The author has chosen them, the words that is, carefully, so that, when seen all at once, they produce an image of life that is beautiful and surprising and deep. What we love in our books are the depths of many marvelous moments seen all at one time." Unquote. Will quantum science also create this sense of simultaneity, just as the literature of the Tralfamadorians describes it?
I think this is a very beautiful and poetic picture. I think simultaneity, in a sense, is exactly what in quantum physics would be called superposition. So the fact that something can be two things at the same time. So in that sense, I think the image from the Vonnegut book is really not so wrong or not so different from what we try to achieve in quantum science. And in that sense, there is a beauty, of course, a poetic beauty also to quantum science, because it allows us to understand the universe to a degree which is very, very high. But on the other hand, the very basic of quantum physics has not been understood. So there is a poetic sense also in there. And I think in any case, there is a strong link between science fiction and academic research. Science fiction tends to explore, perhaps not in the Slaughterhouse-Five novel so much, but in general, of course, science fiction tries to explore how society will change, assuming that a particular material has been made, a way of transport has been invented. And this, of course, is what we call impact in our research. How is society going to change as a result of the research that we do? What is different, I suppose, is that the work that we do is not fiction. It is trying to make the science reality.
You just hinted at some of the practical results of your work. Can you explore on that a little further?
Yes. The successful development of quantum technologies has the potential to really change society. Not necessarily for the better or for the worse, but to fundamentally change it. In some cases, the change will not be disruptive. If I am able to implement quantum sensing, it will be much easier to sense electromagnetic fields, which has a strong biomedical application. Being able to image brain currents, we understand better the brain, we can heal patients. Being able to sense particular molecules in someone's breath will perhaps allow us to diagnose illnesses. And this, of course, is purely beneficial to humanity, not necessarily leading to a disruptive change. Things like quantum computing do have this potential in the sense that one of the main use cases of quantum computing is prime factor determination. This might sound like an academic exercise, but our encryption algorithms, the fact that we can order something online and we can transmit our credit card details without somebody listening in, these encryption algorithms are based on the fact that prime factorization is not possible. With quantum computing, this would be possible. And this, of course, would change society because we would have to invent new ways of secure transmission of data, which is where another quantum technology, that of quantum communication, may actually provide the solution. Because it can be shown, and first results show that it is actually possible to transmit information, which is, by definition, foolproof and cannot be intercepted by other parties.
As for the practical results that you just referred to, how's the cooperation with industry in this field going? What interests do you experience from industry? And actually, how do you cooperate with industrial partners?
Frankly speaking, the interest of industry in this field has exploded over the past 10 years or so. Whereas before, one would try to cooperate with a spin-off company of the university to try and find practical applications of the basic research that we were doing. Now, in a certain sense, it is the other way around. In quantum computing, there are major companies that, out of their own initiative, fund research groups or develop their own quantum computers. For example, in Eningen, close to Stuttgart, there is a quantum computer made or developed by a company, which is now put at the disposal of people to use this, actually. So you see this inversion of the academic scientists trying to get the interest from industry to industry actually going to academic partners to help them with the development of products that they find interesting. Quantum sensing is another story where already now there are discussions which are very, very far advanced of bringing to market quantum sensors. And this is certainly something more on a timescale of months than on a timescale of years. So there has been an enormous interest, and it does not look like this is waning of industry for this research.
You have come to the University of Stuttgart a little over 10 years ago. And earlier, you already hinted at society and the effects of your research of you and your colleagues in this field for society. Can you give us a sketch how society would react to your research results in the coming 10 years?
Yes, I think what we will see in society is, first of all, a certain understanding or acceptance that some of these new technologies are going to play a role. Of course, we as academics try to ease this process by reaching out to the general audience, making podcasts, but also making exhibitions. We will make an exhibition at the Stuttgart City Hall, and so on and so forth. We are putting lots of effort in these endeavors. Certainly, groups at the University of Stuttgart have done this over many, many years now. After this understanding or awareness of quantum technologies, I would say, will come acceptance that these things exist, that they are maybe very difficult to understand, but that these things actually work. And I think society in general is very flexible when it comes to these things. There are many technologies or things that have appeared over the past years that have the potential to change society in very fundamental ways. I just name ChatGPT as an example. And I think society is already on the way to adapting to things like ChatGPT, deepfakes, and so on and so forth. So I have no doubt that society will also adapt to the advent of quantum technologies and the changes that it has the potential to have on society.
And in this very context, how should university education and educational programs in your field be structured to meet the new challenges and requirements?
I'm strongly in favor of regularly overhauling study courses to make sure that what we teach is actually relevant to today's society. And I think most university academics are very willing to do so. Of course, there is a normal resistance, I would say, to change. But this is not necessarily a showstopper. Of course, there is increasing administrative burdens. It is increasingly difficult to find research funding. So we have to move within these boundary conditions. I think one of the key points beyond developing the curriculum is also diversification or diversity in teaching, different methods of teaching, but also addressing different types of students. So far in Stuttgart, the majority of chemistry students are from the Stuttgart area. But now, for example, we are implementing an international master course in chemistry where we hope to attract many international students. I think this is a fantastic development because with these people from abroad will come new cultures, new insights, which will certainly lead to other people that have previously not had access to these things, also doing their studies at Stuttgart and then later on, of course, perhaps doing their PhDs in Chem for Quant relevant topics.
Towards the end of our conversation, I have 7 short questions to you. We call this Moment 7. Please answer them as shortly as possible. Moment 1. Spätzle or Maultaschen?
Maultaschen.
Moment 2. One thing you could change about the world would be?
People talking to each other.
Moment 3. Do you have a book recommendation for us?
I would recommend a book which is called Geschichte der Völkerwanderung. So it is the history in between, let's say, the collapse of the Roman Empire and the advent of Charles the Great, which is, of course, a very obscure period in history. And what this book says is that what we now consider normal, that there are nations that have certain identities and they are somehow in conflict with each other, is absolute nonsense, because what this book shows is that at some point a certain group of people agree on their myth of origin and then call themselves a nation. They do not need to be genetically related to each other at all. And that, I think, shows that many of the conflicts that we have in current society are based on such myths and not on reality.
Moment 4. The best advice that you have ever received was?
To move on when it's time.
Moment 5. Your favorite place on campus here at the University of Stuttgart is?
The Pfaffenwald.
Moment 6. Please finish the following sentence. If I could start all over again, I would do the following differently.
Not very much. I'm quite happy.
And moment 7. Please complete the sentence. Thanks to my studies, I know that...
I am in the right job.
Thank you so much for our conversation and also for having taken the time today. Most of all, wishing you and your research group every possible success in your future work and upcoming projects. And to our audience, it is always good hearing from you. Stay healthy, stay good, and stay tuned for our conversations that are always based on what is made in science. My name is Wolfgang Holtkamp, and I'm Senior Advisor on International Affairs. Have a great podcasting day.